Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the architecture of scale. In this page, we will cover the fundamental concept of mixture of experts and why it is essential for modern artificial intelligence systems. We are going to take the monolithic models we have known and tear them apart to see how they actually run. As you can see on this whiteboard, we are looking at a complex diagram involving input tokens, routers, and various expert blocks. Some experts are activated, while others remain inactive based on the specific needs of the incoming data. This process involves top K routing and softmax gating to combine the outputs effectively. By the end of this teardown, you will understand how we move from a single dense model to a sophisticated network of specialized components that can scale to unprecedented levels. This is the blueprint for the next generation of large language models and intelligent systems. To understand why we need the mixture of experts approach, we first have to look at the brute force bottleneck currently facing the industry. Traditional models are what we call dense monoliths. For example, to generate just a single word, a model like GPT-4 has to fire all 175 billion parameters simultaneously. Think about that for a moment. It is equivalent to wiring every single light in a massive skyscraper to one single switch. The energy consumption is staggering, requiring 1,287 megawatt-hours of electricity for just a single training run. This leads us to what researchers call the energy wall. If we tried to scale this traditional approach to 1 trillion parameters, it would require 250 100 GPUs just to load the model into memory. Physics and thermodynamics simply will not allow us to continue with brute force scaling. We have reached a point where we must build lazier, more efficient models to move forward. The solution to the energy wall lies in the sparsity imperative and biological efficiency. There is a common mentorship quote that says you should not fall into the trap of the 10% brain myth. In reality, the brain uses everything, just not all at once. This is the core principle of dynamic context. When you are focused on solving a calculus problem, your visual cortex effectively sleeps because it is not needed for the task. This allows the human brain to operate on a tiny 20-watt power budget through dynamic sparsity. We can see this reflected in Marvin Minsky's Society of Mind from 1986, which posits that general intelligence is actually an illusion created by millions of specialized, narrow experts voting at the speed of thought. By identifying active nodes for specialization and keeping dormant regions for efficiency, we can mirror this biological topology in our silicon systems to achieve much higher levels of performance with significantly lower power requirements. In our first exploded view, we look at the process of splintering the feed-forward monolith. In a standard transformer architecture, we replace the dense feed-forward layer with a number of independent and identically initialized expert subnetworks. It is important to note that the attention layers remain shared across the entire system. Only the key value memory blocks are splintered into these separate experts. A crucial detail to remember is that you do not pre-label these experts with specific tasks like math or coding. Under the hood, the network must discover its own specializations during the training process. As the model learns from data, different experts will naturally begin to handle different types of patterns. This self-organizing behavior is what allows the model to become more than the sum of its parts. By breaking the feed-forward layer into these pieces, we allow the model to selectively activate only the most relevant knowledge for any given input. The second exploded view focuses on the gating network, which is the brain behind the routing. The router has one specific job: generating a probability distribution for an incoming token. This is represented by the mathematical function g of x equals softmax of x multiplied by wg. Here, wg is a tiny and incredibly fast matrix compared to the massive size of the expert blocks. It acts like a high-speed switchboard that directs traffic. Because every token must pass through the router before reaching an expert, latency is absolutely critical. If the router is slow, it creates a bottleneck that slows down the entire sparse architecture, regardless of how fast the experts are. The router must make a split-second decision to ensure the token reaches the right destination without wasting compute cycles. This tiny component is the traffic controller that makes the entire multi-expert system viable in a real-world production environment. Our third exploded view explores top K collaborative routing. Not all routing is created equal. For instance, top 1 routing used in the switch transformer can sometimes miss subtle linguistic nuances. Modern high-performance models like GPT-4 and Mixtral often utilize top 2 routing, which allows the model to blend multiple viewpoints for a single output. The math shows that the output for a token is the sum of the gate scores multiplied by the expert outputs for the top 2 selected experts. Think of it as a proportional democracy, where we are weighting the answers of the experts by their router scores. If expert 3 has a weight of 0.7 and expert 6 has a weight of 0.3, the final result will be a combination that favors the more confident expert while still incorporating insights from the second. This collaboration allows for much greater flexibility and helps the model handle complex queries that might span multiple domains of knowledge. We now encounter the lexical paradox. Specialization in these models is emergent rather than logical. Experts divide themselves based on strange mathematical realities rather than human categories like history or math. The training process discovers statistical regularities that a human taxonomist would never think to invent. For example, one expert might focus on a specific punctuation mark, a French word, and an Apple icon, while another handles specific code blocks and architectural imagery. We should never attempt to hand design or force these expert categories. Instead, we must let gradient descent find what we call the alien logic of the data. When we look at these buckets of knowledge, they might seem random to us, but they represent the most efficient way for the neural network to categorize the information it has processed. This emergent behavior is a hallmark of truly powerful sparse systems that have moved beyond human-defined limitations. Every system has a failure point, and for mixture of experts, it is the load balancing problem. This is a critical issue that can keep engineers awake at night because it fails silently. If one expert happens to get slightly better than the others early in the training process, the router will naturally start sending it more tokens. Because it receives more tokens, it gets more gradients, improves even faster, and eventually begins to hoard all the traffic. This leads to expert collapse, where the other experts become functionally vestigial and stop contributing to the model. You are then left with a slow and memory-heavy dense model in disguise. The diagram shows expert 3 becoming a massive bottleneck while others sit idle. This traffic hoarding creates a critical failure where the benefits of sparsity are lost. Preventing this requires careful management to ensure that all experts are utilized effectively and that the workload is distributed across the entire ecosystem. To fix the load balancing problem, we use the patch known as auxiliary loss and shared experts. We add a secondary loss function that essentially punishes the router if it starts playing favorites among the experts. We also use noisy top K gating, which injects a small amount of random noise to force the model to explore neglected experts during training. A very elegant fix introduced by DeepSeek involves isolating universal grammar into a constantly active shared expert. This leaves the rooted experts free to learn obscure niches without having to replicate basic logic that every token needs. The math for the auxiliary loss is a balance between uniform distribution error and a load imbalance penalty. The key takeaway here is that balance is everything. The noise forces exploration, while the shared experts handle the foundational basics, ensuring that the specialized experts can focus on what they do best without being overwhelmed by common tasks. Now let's look at the architecture in production using the famous 8x7b magic trick. GPT-4 used an 8-way mixture of experts to win the scaling race, and Mistral later democratized this approach. The Mixtral 8x7b model has the total knowledge capacity of a 47 billion parameter model, yet it runs at the raw inference speed of a much smaller 13 billion parameter model. This is how you bypass the energy wall. By decoupling compute from parameter count, we achieve massive efficiency gains. In this diagram, you can see that while the total parameters are nearly 47 billion, only about 12.9 billion are active at any given time for a single token. This sparse activation is the secret sauce. It is not magic. It is just clever routing that gives you the capacity of a giant model without the massive compute cost associated with firing every single parameter for every single word. The hardware reality presents us with the VRAM catch-22. While compute might be getting cheaper, memory remains unforgiving. Even though the router decides which experts to use at inference time, you must keep all 33.8 billion dormant parameters loaded in VRAM because the system doesn't know which expert will be called next. This creates a situation where a model that computes like a 13 billion parameter model still requires 90 gigabytes of VRAM to function. We survive this challenge through techniques like 4-bit quantization and aggressive expert offloading to CPU RAM. The diagram shows the experts sitting in memory like blocks on a rack, some sleeping and some active. If you don't have enough VRAM to hold the entire ecosystem, the system slows down significantly as it swaps data back and forth. This hardware constraint is the primary hurdle for running large mixture of expert models on consumer-grade equipment today. Looking toward the future, we see frontier architecture focused on hyper-sparsity. Researchers are asking what would happen if you had 1 million micro-experts instead of just 8 large ones. This presents a new challenge because standard softmax routing breaks down when you reach 1 million options. To solve this, Google's peer architecture uses maximum inner product search, or MIPS, to retrieve experts in sublinear time. It functions essentially like a search engine for neural weights. Instead of checking every expert, it quickly identifies the most relevant ones. This moves us away from having a small committee of experts toward an entire digital civilization of specialized micro-components. The router acts like a spotlight, finding exactly the right tiny cubes of knowledge in a vast sea of data. This level of granularity could lead to even more efficient and capable models that can store vast amounts of information with even less active compute. Another frontier architecture is dynamic continual learning. Standard dense models often suffer from what we call catastrophic forgetting when they are fine-tuned on new data. They lose old information as they learn new things. Bio-mixture of experts proposes a solution by spawning new, blank experts on the fly whenever the router encounters a knowledge domain it hasn't mapped yet. This is neuroplasticity in silicon. It allows the model to grow new synapses and integrate new information without destroying the old routing weights or original knowledge. In the diagram, we see the system identifying a gap in its knowledge and spawning a new expert block to fill it. This non-destructive integration is key for models that need to stay relevant over long periods of time. By adding capacity only where it is needed, we can create models that keep learning and expanding their expertise throughout their entire life cycle without ever needing a full retraining. Finally, we have the philosophical teardown of the singular I when you chat with a mixture of experts model. You are not actually talking to a single entity. Instead, you're talking to an ever-shifting mosaic of networks passing the microphone at light speed. Our own human attention can be viewed as just a biological gating network. The sense of a single I that we feel might just be an illusion created by the coordination of different brain regions. We can compare the digital router and its experts to the biological prefrontal cortex and its specific regions like the motor cortex, visual cortex, and Broca's area. As researchers build these systems, they are finally taking the theories of pioneers like Minsky seriously. We have to ask if human consciousness is just a very advanced router. Understanding how these artificial ecosystems work gives us profound insights into how our own minds might be organized as a collection of specialized agents working in concert. The final sign-off from the senior engineer is simple: distributed specialization always beats brute force. Whether we are looking at biological minds or artificial ones, they are not monoliths. They are complex ecosystems. The miracle of intelligence isn't building one enormous, all-encompassing brain. It is the art of orchestrating 1,000 small, specialized ones to work together seamlessly. As we move forward in the field of AI, the focus will continue to shift away from just making models bigger and toward making them smarter about how they use their resources. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.